Alright, ladies and gentlemen, in this lesson we're going to start looking at derivatives and kind of how derivatives play a role in physics. So we're going to mainly look at derivatives in kinematics and kind of talk about derivatives. So you say derivatives, I thought we only did that in calculus. Why do we care in physics? And I would say take a step back and think about what a derivative actually does functionally in calculus. It really does a few different things. It calculates the slope of a function, which may or may not be all that useful to us. It determines the rate of change of a function. Well, that is certainly useful to us in physics. Something like velocity and position. Velocity is the rate of change of position, or acceleration is the rate of change of velocity. So there should be some derivatives in velocity, acceleration, and position. It can also be used to find maximum, minimums, points of inflections. We can think of lots of situations where you might want to find like a maximum. What's the maximum height this ball flies? Well, that could be a helpful thing to have a derivative to do. I can figure out what time that should occur and then plug it back into the position equation to figure out what that position is. It tends to work out that there are lots of uses for derivatives in physics. Basically, any situation you have a rate of change of one variable compared to another variable, you can define a derivative for that situation. So what I do is go through some basic rules of differentiation that you've probably seen before. The power rule is probably the most basic derivative rule. If you have x to the n power, and you want to take the derivative of that, find the rate of change of that function, you get n times x to the n to the minus 1 power. Three other ones that are common that we come across are sine and cosine. The derivative of sine is cosine. The derivative of cosine is negative sine. What this means is if you do the second derivative of sine, do derivative twice, you get negative sine. That's a helpful thing to have in the back of your head, because if you take the second derivative of a function and get negative the function spit out of it, that tells you that the function must be sine or cosine. Another one that's a common one, derivative of e to the x is e to the x. So if you get a function, you take its derivative and you get the function popping back out, you know it's an exponential function. And the last one that's kind of an odd one is derivative of the natural logarithm is 1 over x. So these are some basic differentiation rules that we have. Now if we look at probably the most common, or at least the first two examples of derivatives that we come across in physics, I would say look at displacement, velocity, acceleration. Now if we define average velocity, I would define it as displacement divided by time, delta x divided by delta t. If I defined average acceleration, I would call it delta v over delta t. Now, these work well if I'm trying to figure out on average what are things doing, but they don't work well if I want to know at any given specific point in time how fast is the object moving, what is its acceleration. So in order to answer this question, we ask ourselves what happens if delta t gets really small. Now, in calculus, you might set this up as a limit as delta t approaches 0, and then figure out what happens to that function in that if you work out that limit. Well, here we go. What actually happens as you work this limit out is you end up with what's called a derivative. Take the derivative of x with respect to t, and you get velocity. Happens to work out that you get the exact same thing for acceleration. If you take the limit as delta t gets really small, well, you should recognize, oh man, that's a derivative. A equals the derivative of v, or acceleration is the time derivative of velocity. So let's look at the kind of standard toolbox kinematics equations, and here's position as a function of time. If we differentiate this, well, the first one, a constant, becomes 0. v0t becomes v0. Half at squared becomes at. And what you end up with is v of t equals v initial plus at. Well, if we take the derivative of this thing, well, the v0 is a constant, 0. At becomes, well, just a. And so this would say my equations for constant acceleration, yeah, it works. That the derivative of x, or displacement, looks like velocity. The derivative of velocity looks like acceleration. So let's look at a problem, and I've got problem E1 here. Let's say the displacement of a particle is given by the function x of t equals 4t squared minus 5t plus 2, and I want to figure out a function for the velocity of the particle, a function for the acceleration of the particle, and what is the velocity at times t equals 3 seconds. So the first step, take the derivative of the position function. If you take the derivative of 4t squared minus 5t plus 2, you get 8t minus 5. Now in order to find the acceleration, take the derivative of the velocity function. 8t minus 5 becomes 8. Well, in order to find the velocity at times t equals 3 seconds, plug in 3 into your velocity equation. 8 times 3 minus 5 gives you 19 meters per second. So derivatives are one way you can begin to derive that set of equations, position, velocity, and acceleration, and prove that the toolbox works in a different way. Usually the way I prove the toolbox works is to start with the definitions of average velocity and average acceleration and build the toolbox out of those definitions. You can start with the 1/2 at squared plus v0t plus x0 and prove the other ones are true. There are a couple of other useful derivative rules that we come across on a regular basis in physics. One of them is the product rule. What if I have a function of x multiplied by another function of x? How do I differentiate those? Now, it's one thing if those two functions easily multiply, like say x plus 2 and x squared plus x. Those easily multiply, you can FOIL it out and take the derivative of that perfectly fine. It's a little bit more difficult if you have something like e to the x times sine of x. There you have two functions of x multiplied by one another that don't really have a good way to multiply them before you differentiate them. And so there's the rule there. What you do is take the derivative of the first function multiplied by the second function, add this first function multiplied by the derivative of the second function. A related one is what's called the quotient rule. What if you have a function of x divided by a function of x? So maybe you had sine of x divided by e to the x. What will we do? And so here's the rule we have here. Derivative of the first times the second minus the second, or minus the first times derivative of the second all over the second squared. And then the last one is the chain rule. What if I have function of x, or function f, which has another function of x inside of it? Maybe sine of e to the x would be a good example. Well, then you take the derivative of the outside function, keep the inside function the same, and multiply it by the derivative of the inside function. It's worth pointing out with the chain rule that you could have h of f of g of I of j of x, have all these functions together, and you just apply the chain rule, just keep going inside the parentheses. So let's take a look at Newton's second law. Newton's second law is kind of interesting because if we apply derivatives, we can actually come up with an explanation for what do we do if f is not constant. Well, you guys probably already know that f by impulse momentum theorem is delta p over delta t, or dp over dt, the change in momentum over the change in time. This is actually the way Isaac Newton would have written Newton's second law. If we rearrange that and just say the masses of the objects must remain constant, well, we can prove that that is Newton's second law, that F equals ma. But what if mass could change too? Things become a little bit more complicated. So a situation where the mass of an object certainly changes as it accelerates is something like a rocket being launched. In the case of a rocket, probably about 90% of your rocket's mass to begin with is fuel that's going to get burned up during the course of the rocket's flight. So what if we had dmv times dt? Well, I could apply the chain rule to figure out what happens. That m dv over dt plus dm over dt times v is equal to f. This becomes a little bit more complicated because I now need to know both the derivatives of m and v and both the functions of m and v. How is m being used up? How is v changing? And so this becomes a much more complicated problem to work out. So another thing that we use derivatives for in calculus is what I call the derivative tests. And the two derivative tests that I have are the first derivative test and the second derivative test. So in the first derivative test, if you find a place where the first derivative is 0, we are at either a maximum or a minimum for that function, a relative extrema. Now, if you have a first derivative and it's greater than 0, the function is increasing at that value of x. If you have the first derivative and you plug in x and you get something less than 0, the function is decreasing. Now, for the second derivative test, if you get the second derivative be 0, you're at an inflection point. What that means is you're changing from concave up to concave down. If the second derivative is greater than 0, you have a concave up function. It's something that looks like it opens up. I call these happy functions because it makes smiley faces. If you have a second derivative that is less than 0, that's a concave down function. That's something that opens up downward. Those are what I would call the sad functions. They make frowny faces. So let's take a look at a function here, and let's say we have a 1 kilogram particle experiencing a single conservative force, f of x, as it moves along the x-axis. And let's say we define the potential energy associated with this force as given by the function negative 4x e to the negative x over 4 power in joules. And it says at 5 meters, the kinetic energy of the particle is 2 joules. And we want to answer 3 questions. Determine the total mechanical energy of the system, determine a function for the value of f of x, and then find the places where the particle is in equilibrium. Now it's in equilibrium where f of x is 0. So the first one, well, if I know the kinetic energy is 2 joules at x equals 5 meters, I should probably find the potential energy at x equals 5 meters. Because the total mechanical energy is potential plus kinetic. So if I plug in 5 meters into my potential energy function, what I get is that the total potential energy is negative 5.7 joules. So when I actually go to calculate the total mechanical energy, I get negative 3.7 joules. Now, don't be concerned that we have a negative value for total mechanical energy or a negative value for potential energy. It just means that we've defined 0 potential energy in a way that this is some energy below that definition. There are lots of scenarios where you calculate the total mechanical energy and get a negative number, or the total potential energy and get a negative number. 2 scenarios that I can think of right off the top of my head. The gravitational pull of a planet or star on things that orbit it. We generally would define the gravitational potential energy in that case as a negative number. And the second one from chemistry, if you think of how the electrons are held to the atom, we generally define the potential energy in that system as negative 2. That removing the electron from the atom and moving it far away is a potential energy of 0. So second one, determine a function for the force, f of x. Now happens to work out the force and potential energy, as you probably are aware at this point, are related to one another. That if you have a potential energy function and you want to find the force, find the slope of the potential energy function. And in fact, here we go, that f equals negative d dx for the potential energy function. So I want to take the derivative of potential energy and then multiply it by negative 1. So I have something that looks like the chain or power rule. First times derivative of the second plus derivative of the first times the second. So I get 4x e to the negative 4x. Have to apply the chain rule negative 4th. And then add 4 plus e to the negative 4x. And so what we end up with is negative x times e to the negative x over 4 plus 4 e to the negative x over 4. And so if I kind of factor that out, I get 4 minus x e to the negative x over 4 is the function for force. One thing to point out, I did distribute this negative sign right here and made this a positive, and then this, well, a positive because this negative would come out here. And so those do get distributed in there. If you work this out, you'll get it the correct thing. So the last question, find the places where the particle's in equilibrium. I want to find places where the force is equal to 0. So I'm going to set my function for force equal to 0. And here I have 4 minus x times e to the negative x over 4 power equals 0. Well, for that to be true, either 4 minus x must equal 0 or e to the negative x over 4 power equals 0. Now, on the left-hand side, that's true at x equals 4 meters. Solve for x, that's what you get. On the right-hand side, e to the negative x over 4 only becomes 0 if you made x an infinitely large number. So just by looking at this, it tends to suggest to me that making my potential energy 0 at an infinitely large number is probably what they did here. So let's get a quick overview of derivatives and some places where we might use them in physics. As we work through the course of this course from now on, you will see me plug in things in derivative form. We will take some time after Thanksgiving break and really hammer down things that are derivatives or are related to derivatives of functions and how we work out those types of problems in physics.